Okay, hi everybody, my name is David and I'm a PhD student at Imperial College London. I'm under the supervision of Tony Phil, and today I'll be talking to you about performance test-driven development in real time. This is a piece of work that we've been doing in close collaboration with Rob Shatley. They both couldn't make it today, unfortunately. They both have teaching duties, but no one's going to miss a PhD student taken out of the office for a day. So, first things first, why is performance testing important? Well, the first thing is responsiveness. So how long does it take to service a request, to load a page, to return with an answer? Consumer applications are very sensitive to responsiveness because people are very impatient. Even a small change in responsiveness, it can feel much longer than it actually is. For kind of server applications, the equivalent would be throughput, or how many jobs can you service within some time frame. Second thing is scalability. When we add additional computational resources, how many more users and how much more load can our system handle, and what are the effects on response times. And the third thing is stability. So what happens when there is a sudden surge in number of users or load, at which point in our application do we start to see requests being dropped or they can start hang. So performance testing can kind of help to answer these questions and to make sure that these requirements are met. So modern software generally is built using some form of agile development process, which involves iterative cycles of design, development, test, and release. Each cycle typically spans a time period anywhere between several weeks on the upper end down to a single day. Performance testing is at best done prior to every release, but it's usually something that's kind of done separately. At worst, it's completely ignored, and this is quite common for software that's kind of in the early stages of development, so things like startups and such. Where a priority is placed on adding new features and getting the release out there. So it's not actually uncommon for performance issues to kind of creep up after release. They can be reported as bugs or customer complaints. Although parametric optimization is said to be the root of all evil, not thinking about performance at all can lead to designs that have fundamental scalability issues, and these can manifest further down the line where it's more extensive and difficult to fix. So we currently use tools such as JMeter or the Grinder for Java. These tools generate load on the system and record performance metrics. This is usually a fairly extensive process in terms of time and resources, which is partly why it's something that's kind of done separately. When it comes to functional requirement testing, we've come to recognize that it's very important and be left as an afterthought. We now employ different types of functional testing alongside development with varying granularity. So for example, unfortunately you can't really see the text, but it should say unit test here and integration test here and acceptance test here. So we employ these kind of different types of site development, and it's kind of integral to the agile development process. So in test-driven development, or TDD, we kind of take functional requirement testing a stage further by writing unit tests first before we actually write any code. These unit tests are small, they run very quickly, and they are designed to fail such that a developer writes the bare minimum amount of code needed to make these tests pass. The just passing code is then improved upon during the refactoring process, and this cycle is called the red-green refactor cycle. The key idea, I think, behind the TDD process is that by writing the tests first, it can actually help developers kind of drive the design process, and it acts as a form of documentation, so developers can think about the API, the design of that API, and it's not something that's just done for verifying software. So our idea is to bring performance testing forward in the software development cycle. So rather than doing it kind of separately, what if we could integrate it alongside development, parallel to unit and integration testing for functional requirements? So we'd like developers to be able to write tests that kind of provide assurances on the performance characteristics of the objects that they are developing before they actually commit any code into source control. And in a similar way to TDD, we hope that when developers write these tests, it will help them think about the design of their objects and think about what kind of performance they need from neighboring dependencies. So to kind of illustrate, sorry, the projector doesn't seem to be really projecting much there. To kind of illustrate, we'll be using an example application throughout this talk. It's called Tweeter. It's a simple micro-blogging web application. It definitely bears no resemblance to a similar sounding bigger cousin. So Tweeter it's built using a pretty standard model view controller pattern in Java. It uses the Spring framework, and then it uses a database to store persistent user data. So the client sends a request to the dispatcher, which is then forwarded to a controller. The controller renders a model, which is an abstract representation of all the data that a view needs. To do this, the controller might use external dependencies. So in our particular example, we have a security service, a user service, and a message service. So the security service provides authentication, and both user service and message service provide an interface for retrieving and storing data from the database. Once the view is ready, it's rendered by a template engine and returned to the client. Here is a code fragment showing what a controller method for our application looks like. On line 4, the annotation auto-wire, it's a string annotation for an object's dependencies. So string will automatically take care of instantiating these dependencies and wiring them together. On line 7, the annotation request mapping is what actually maps a URL to a controller method. So when the request is made to that URL, the dispatcher will use this annotation to make sure it's forwarded to the appropriate method. And on line 9, we can hopefully see that most of the actual work is done by a message service using a method called getPublicTimeline. So this method basically returns a list of the most recent post messages, which is the data needed by the view. On line 10, we attach this to a model, and finally we return the view to the client. And string automatically takes care of wiring the model to the view and rendering it using a template engine. Message service is an interface that provides methods for retrieving and publishing messages. Implementations are database specific. Our particular implementation uses a Cassandra database, and here is a code fragment showing the implementation of getPublicTimeline. The driver provides an interface called Cassandra operations. It has basic standard create, read, update, and delete operations. It also provides high-level mapping between table rows and annotated plain Java objects. So in this particular case, each message corresponds to one row in the table messages. So our getPublicTimeline implementation builds a query, executes the query using the driver to retrieve the results, sorts the results according to their timestamps, and returns it to the controller. So what would a unit test look like for our application? Well, for a unit test, we want to focus on one particular object on the test. And for us, it makes sense to look at the controller, since it's the core of our application, it ties everything together, and it's the place that we can, where we have the most agency to make changes. So remember, the controller has several dependencies. In a unit test, it could be difficult, impractical, or too slow to use real instances of these dependencies. For example, these real instances might behave in non-deterministic ways, so it could be retrieving volatile data from a database, or functions could be wall clock time related, and you definitely don't want to insert actual rows into your database for when you run your tests. These dependencies could represent things like databases, but also web services or other processes or things over the network. So that means they're too slow to use in a unit test, which must run very quickly. And finally, these dependencies might have further dependencies of their own. So in our case, both user service and message service use an instance of Cassandra operations. So in a unit test, it's usually impractical to kind of fully instantiate all the dependencies. In functional unit testing, we get around this by using mock objects. Hopefully, most of you are kind of familiar with what they are and what they do. For those of you who aren't, mock objects, they're used to simulate the external behavior of an interface, and it's done in a deterministic way so that they can be used in tests. You do this by setting expectations on the mock objects, which specify how many times a particular method should be invoked by your object on the test. They can also be configured to return expected results. So these expectations together are used to assert how an object on the test should behave. So here is a code fragment showing what a small unit test might look like for our PublicTimeline method. This is written in JUnit and JU. For those of you who are not familiar with that, other testing frameworks should look something similar. So on line 2, we create something called a mockery. This is just a factory for making mocks and setting expectations on them. Next, on line 5, we use the mockery to create a mock of message service. Note that you can only mock interfaces because it uses the Java dynamic proxy library to actually create the mocks. On line 6, we are creating a real instance controller by passing in the mock dependencies, which I've omitted due to space constraints. And on line 7, we make any additional parameters that are needed by our controller. In this case, it's an MVC model, which is just a key map store. On lines 9 and 10, we set expectations on our mocks, and those of you who are not familiar with JMock 2, this might look a little bit weird. It's kind of like a mini DSL. But what it's essentially saying is we expect the controller to make exactly one call to the message service method get public timeline. Finally, in our test, we make the actual invocation to the controller method. So now that we've seen what a unit test looks like, what does a performance unit test actually mean? So in a real application, we would time the execution time of a controller method like public timeline by deploying it on some kind of test production environment where we can then measure wall clock or CPU time. If we can't do that, then we need to at least have a real database that we connect to on our dev machines and then kind of time how long it takes to run the method. So what we would like to do in a unit test where we're using a mock, obviously we can't just time the execution of the mock object because it kind of bears no relation to the real thing. A mock will run very quickly because it's emulating the external behavior of an object. When you're actually accessing a database, it will be much slower. So for performance unit tests to work, we need to be able to kind of predict the performance of whatever interface or system that the mock object represents. When we call a mock object, the testing framework will check the invocation against the list of expected invocations, and it will return expected results, if any. So we introduce a new thing called a performance model, and this is used to predict how long a particular invocation will take. And the test framework then takes that predicted value to update the execution time of the test. Now, a performance model is a fairly abstract representation of a system's performance characteristics. You can think of it as a magical black box that can just answer how long a particular invocation will take. Models can vary in complexity, where generally more detailed models will give you more accurate or more representative results, but will be more difficult to use. It could be as simple as a statistical model, which samples random numbers from a probability distribution. It could be sampling measured performance data from a real production environment that you've captured using tools like JMeter, Lambda, Nagios. It could also be formal modeling languages, such as queuing networks, and things like Petri nets. So in the academic software performance engineering community, a lot of effort is spent on creating models for systems, and these are very sadly underutilized by developers in industry, and that's partly due to a lack of tooling to integrate them with real code. So our goal is to kind of bridge the gap between research and industry by seeing how we can make these models more useful by developers. And by doing so, we hope to learn from you guys, hopefully, what it is that makes models useful and hold academic researchers more accountable when evaluating models. So often models are simply evaluated based on their predicted accuracy, which I think is lacking. We also want to evaluate how useful they are to developers, because, yeah, that's why they're not used very often. And our work so far has led to something called perfmock, which is an extension to the JMock 2 library for Java. So this allows developers to write performance unit tests by configuring mock objects with performance models. It's backwards compatible so that normal unit tests will continue to run without change. It times the execution of these unit tests by interleaving real time that is spent running code and virtual time that is spent running models. It provides a range of statistical assertions which allow developers to specify upper bounds on the execution times of tests. It provides a number of off-the-shelf models for developers to use, and it comes with building blocks that let them create their own models. So now I'll demonstrate how to write a performance unit test using perfmock, and possibly how to integrate it as part of the software development process. So in our original unit test, we have a mock grid object, which is a factory for making mocks. We simply replace this with something called a performance mock grid, and it's a simple drop-in replacement. Originally, we used the mock object. We pass in an interface that we want to make a mock of. And perfmock adds a second optional parameter that allows you to specify a performance model for this particular mock. And perfMock allows you to kind of plug in any model that conforms to a particular, that conforms to the performance model interface, because as we've discussed previously, a model is fairly abstract and can have many different implementations. So for our particular example, we will use a simple normal distribution to model the performance of our message service. Now, most models will have some kind of parameters to kind of specify how to set parameters depends on whether the dependency that we're mocking exists or not. So if it doesn't exist, we can think of the parameters as a specification for how we would like it to perform in order to meet our own needs. And if it does exist, then perhaps we can measure to estimate these parameters. In our example, we'll set the mean to 100 milliseconds and the standard deviation to 20 milliseconds. So most performance models, other than the simplest ones that just return a fixed value, will be stochastic. So for example, we could be sampling from a distribution, or we could be sampling from a file containing recorded performance metrics, or there could be probabilistic branching in certain types of formal models. Therefore, it's not very useful to just run a test a single time. So to support this, perfMock provides a new method called repeat, which allows you to run a small test kernel a large number of times, grouped together as a single experiment. So the first parameter is just the number of times to repeat, and the second parameter is the test kernel passing lambda function. So to support this, perfMock provides statistical performance assertions, and this is what allows developers to kind of specify upper bounds on the execution times of tests. So
could you read out the system?
Yeah, I'm sorry, the projector is, or rather I'm using a light font, so that says, assert that context.runtimes has percentile 80 less than 150. So what this is saying is we expect that the 80th percentile execution time to be under 150 milliseconds, and that will be kind of asserted against the list of all your repeated tests in one experiment. Okay, good. So hopefully that demonstrates that it's fairly straightforward to kind of go from JUnit unit tests to performance unit tests. So an important question is what values should we use for performance assertions? And this is where there's a lot more flexibility, because it really depends on how developers and teams kind of approach performance. It's not like functional requirements for testing where there is a right and a wrong. It's much more fluid and dynamic. So a few thoughts. They could be set deliberately tight so that even when you make a small change, the test will start to fail. The idea behind this would be to kind of force developers to think about the impact of their changes on particularly sensitive objects in that application. Alternatively, you might be able to use design specifications or perhaps service level agreements to set these assertions. So we run the tests and it passes, which is not surprising because we used a mean with a mean of 100 and a standard deviation of 20, so we would expect that the 80th percentile is under 150. Once we have these tests in place, we can kind of continue development. So this is supposed to be a screenshot of Twitter, where we want to implement a new feature, such as the ability for people to add replies to particular messages. So as we kind of make changes to our application, and particularly when we add new features, we may find that the performance tests that we've written will start to fail. So there's several things we can do to kind of fix that and to make the test pass again. The first thing we can do is we can actually adjust the assertions themselves. Whether this is acceptable or not depends on how teams use assertions and how they were originally set. So usually during early development, it's usually okay to kind of loosen these assertions in exchange for new features. But again, it's up to developers and teams to kind of decide whether or not that's acceptable. It's worth noting that there are other parts of the system where you can kind of gain performance if whatever you're changing is slowing performance. The second thing we can do is adjust the parameters to the performance model. What this means is that we are changing the performance characteristics of an object's dependencies. So, as an example, in our Tweet application, it might mean speeding up queries to our Cassandra database. Perhaps we can do this by changing the way that the database is configured, or we can add additional nodes, or perhaps we can change the way that data is modeled in the database so that we get more performant queries. But if these dependencies don't exist, which is often the case with CDB, it means we're changing the specification, the performance specification of the dependency. And this is actually really cool because you can actually use this to drive the design and development of those dependencies when the time comes, and you can always kind of shift the lens of your performance unit tests downstream to your dependencies. Once you do that, you can then reasonably repeat the process for further dependencies downstream. If the dependencies do exist, then perhaps we can contact the developers or teams responsible for them and send feature requests to see if they can speed up those dependencies in order for us to meet our own performance needs. The last thing we can do is to change the objects directly. So since perfmock also measures CPU time spent running real code, perhaps we can use faster algorithms and kind of gain performance there. If that's not possible, then perhaps we can look into reducing the number of calls to external dependencies. And I mentioned this kind of briefly earlier, that by writing these tests, we hope that developers can kind of think about the designs of the objects that we're testing. So what we have done is we have a library that allows developers to write performance unit tests. These tests run in near zero time, and they can test the performance characteristics of objects in isolation. By using assertions, they can provide some confidence about the performance of something before it's even committed into source control. And because it's part of JUnit, it can integrate with automated building testing systems. So obviously when we deploy our application on a real environment, hopefully there'll be lots of users, and these users will be contending for the same finite resources. So for unit tests, we can reasonably write different tests for the same object by using different parameters or by returning different results to see how our object under test behaves differently. So we want to do something similar with performance unit tests, where we can write many tests that have that kind of simulate different scenarios with different levels of contention to see how that affects performance. And to do so, we need two things. We need a model that can kind of encapsulate contention, and we need some way of generating concurrent load. So to model contention, we have to use something a bit more complicated than a statistical model. In this example, I'm going to use queuing networks. It's a type of formal modeling language, but I think they're pretty intuitive to understand. So the simplest queuing network is a single queuing node. The node has a queue with some size, which is usually unbound, and it has a queuing discipline, which is usually first in, first out. There is a server with a service time distribution, which determines how long it takes to service one request. So requests come into the queue, and if the server is available, it will be served, and if the server is busy, it will join the queue, and according to the specified discipline, if the queue is full, then the request will be dropped. And the lifespan of the request is simply the time difference between a request entering the network and a request leaving the network. And here is an example of a more sophisticated queuing network. So this is a network developed by some colleagues at Imperial, and it models a multi-node Cassandra database. Unfortunately, it's not very clear, but queuing nodes are often used to model contended resources. For example, here network, this is the CPU, and this is the disk. So yeah, the network is usually a number of queuing nodes that are joined together, and requests enter and move around the network, and the response time is when it enters and when it leaves. So now that we have a model that can kind of capture contention, we need some way of being able to generate concurrent load. So remember that in our original test, we used a mock of message service. But let's say we want to use the Cassandra model that I've just shown you. Instead of creating a mock for message service, we instead create a mock for Cassandra operations instead, and then we plug in that kind of queuing network model, and then we use that mock of Cassandra operations to make a real instance of message service. So I think this is important because we're kind of moving away from unit testing territory here, because we're not keeping to an object's kind of immediate dependencies. We're kind of moving downstream slightly. So once we have this, perfmock allows developers to kind of quickly instantiate multiple instances of a unit test. And these instances run in separate threads, but they all use the same queuing network model of the database. So you can think of each thread as a separate user making a request to our application, which then obviously makes a request to the database. So perfmock kind of carefully interleaves time spent executing real code and the time spent in the model. And since it's multiple threads, it actually does this by serializing their execution and using and kind of synchronizing them on a single timeline. I probably won't have too much time to go into details, but it's actually quite complicated. And if you're interested, then please come speak to me afterwards and I can hopefully explain to you. So this is a code fragment showing what a kind of concurrent test looks like that kind of captures contention. So in this particular example, perfmock provides a new method called run concurrent, where you can specify the number of threads to create, and you pass in the same kind of test kernel to use. As you can see, you can nest it inside the repeat method that I've shown you earlier, so you can still kind of have experiments that run something multiple times. I've kind of omitted some of the code because I can't fit it all on one page, but basically this code corresponds to the diagram earlier where we have a mock of Cassandra, and we have a real service and a real controller. And you can see that the expectation here changes to be set on the Cassandra operations mock instead of the message service. So this particular test will return 10 times 5, 50 results, and we can still set expectations on the response times. And as long as the model kind of captures contention, we should see a kind of increase in the response times returned by this test. So we've recently been looking at adding a load generator interface to performance models. So instead of kind of manually creating threads to create contention, the idea is that the load generator will kind of automatically inject background requests into some model before a real request is made. So this means that when a real request enters the model, there will already be background requests moving on the network that cause contention. So doing it this way kind of avoids having to manually create threads. And I guess the interesting thing is the ability to kind of plug in interesting off-the-shelf load profiles. So to summarize, in addition to the short summary earlier, we can now also write we can test different kinds of contention scenarios. And also what's interesting about doing this is that we've just by doing this on our own, we've come to realize kind of the reasons why models aren't used. So the kind of features that are lacking that makes them useful to developers. So one thing is the ability to kind of parameterize implications. So to give an example, the response time of a database query often depends on how much data is returned from the database. And if you look at models for databases, that's 100% of the time missing, because you can't verify models in academia against some kind of benchmark suite with like preset data. So that's one thing that makes them kind of difficult to use by the industry. The second thing that's really interesting is how do you actually tune the parameters to a model? A lot of papers kind of gloss over this fact and kind of hand wave, how to do it. But for models to be useful to people in the industry, there needs to be some kind of clear-cut kind of way or process, or perhaps even a program that can kind of record performance metrics from a real environment and kind of turn that into parameters for a model, which will make it much easier to use. So to wrap up, I'm David, this is my email, and I'd love to hear from you guys what you think might be useful to kind of make models more usable. And that's why Rob and I are very keen to kind of present our work places like this with real developers and not just academic conferences, because we want from you guys ideas about how we can make this more widely used.
Yeah, I appreciated the content as well. I can see this would be useful. Thanks. Yeah. If I just pick one question, it would be, so there's two parts. I use JMOP too, I like it. Mm-hmm. My colleagues are trying to convince me, and they may be successful, that we should use Mockito instead.
Okay.
So I guess two parts to that. One is, I'd be interested in your thoughts of why you chose JMOP 2, and then how much work do you think it would be to fit to other mock frameworks?
Right. So the difference between JMock and other frameworks like Mockito is kind of more of a philosophical one. It's kind of different philosophical ideas of what it means to mock something. So Rob is the expert on this more so than me, and he's the reason why we use JMock, because he's friends with Nat, who's the author of JMock, and yeah, that's why we kind of started our work using JMock. So I think the difference is that with JMock, you kind of have to specify every invocation. So if you make an unexpected invocation, you will actually crash and fail the test, which is not the case with frameworks like Mockito, which only check for kind of positive invocations if you make other calls, and that's considered to be okay. So that's kind of the philosophical difference. As for how much work it would take to port it, it would be quite a lot. It would be quite a lot of work, but yeah, it will be quite a lot of work. So I'm not sure about that. Yeah.
In lots of software development environments,
yes.
or houses, learning how to test is seen as part of the learning process for junior programmers.
Right.
It makes you a better programmer.
Mm-hmm.
It strikes me that the mindset behind being able to specify the design of the tests is a different mindset to that of programming.
Right.
Either, would you recommend it's a separate profession, a separate skill, and therefore a separate team that do this, or do software developers need a different understanding of how to write programs in the first place?
I mean, I can definitely see why, because like writing tests kind of forces you to definitely think about the way things are designed. And I would say that designing software is definitely something that's different to like writing code, right? The art of writing code is kind of different. And I think that a lot of junior programmers go through this because you kind of don't learn that so much at university. I mean, that's something we're trying to change, right? In terms of providing courses that teach our students how to kind of design software. Because like we teach them how to code, and then they go and join a company, and then they're like, oh, like, how do I actually go about designing things? I'm not sure what's correct. Because it's like code like functional tests can pass or fail. It's correct or it's not correct. But design is much more kind of flexible, hand wavy, like as to what is good design and what is bad design. But I definitely don't think it should be separate. I think a good programmer must be able to do both. Right? They must be able to produce good, high quality, clean code, but also come up with good, efficient designs. I don't think it makes sense to kind of separate the two. Cool. Yeah.
I guess we do performance testing in our company, and
right.
In your experience, how representative is normal distributions for modeling response times? How is that totally fake, or how reliable is the normal distribution? Would you say is it?
I think in cases when you don't experience contention, where like where the load is kind of nominal, I think the normal distribution is a fairly good approximation. Okay. It's a fairly good approximation, but that kind of depends on like what you're really doing. Like if you're modeling a database, like I say, the response time is it's often a factor of how many rows you're retrieving. So if you're always retrieving kind of similar amount, like if you're always retrieving a similar amount of data from a database, and you're not really under kind of heavy load, heavy contention, and I think a normal distribution is a pretty good model. Okay, yeah. But I think a normal distribution is only kind of useful for if you already have the system in place. So a lot of performance models, like the complex queue network that I showed you, it's to predict the performance of something that doesn't exist yet. And I think that's the kind of area of work that we're trying to focus on.
Just to sort of pick up on that, and the last point you made about tuning.
Yes.
Given that deploying on real systems is with virtualization and containers in the cloud, it's so automated these days. Is there a direction for your work where you can basically deploy on the real system, measure performance, and update your model automatically to reflect the real situation? Is that a kind of future direction, do you think?
Yeah, that would definitely be the ideal scenario, right, where you kind of take the work out of the developer's hands and kind of automatically provide models. I think one issue with that is model parameters are often very specific to that model, so it's actually quite difficult to generalize some way of automatically generating parameters for like all models. It would have to be something that's like specifically done for each kind of type of model. So definitely work to be done. Yeah.
One here.
Yes.
We are running out of time, but I think we can let it be for a couple of minutes, if that's all it is. So, yeah. Anyone else? No.
Yes.
A specific one. You specify the performance model in the mock
Yes.
creation call,
Mm-hmm.
which is on an interface level,
Yes.
and then you maybe got a mock then it has different methods which may have different characteristics.
Yes.
Maybe they'll code answer this in a low contrast thing that I couldn't see, but presumably there's some way to, you're going to use that mock maybe for some trivial calls that come back with you instantly, and in other calls that they really do have this particular distribution.
Yes, that's a really good point. So currently you can kind of do per method kind of models by implementing your own. You have to create you have to create a model of your own and kind of plug in and say, okay, for this method, I'll use this model. And we'll kind of realize that it's actually quite cumbersome to do. You don't want to do that. So we want to have some way of if you remember the kind of context inside the expectation, where you set expectations per method, we think it'd be good if you can have something there to say, okay, well, for this, we expect to retrieve like 50 rows, and then for this, we expect to retrieve 100 rows. And then by specifying that, you get a different prediction for the performance of that particular invocation. So yeah, almost like search invocation models. Yeah.